Today, we're going to start a short unit on Markov chains. Lots of processes, in algorithmic analysis and elsewhere, can be modeled as Markov chains. One reason that they're especially useful, as we'll see in a future video, is that even though a Markov chain is comprised of a bunch of dependent random variables, they often concentrate as though they are independent. But for this video, we're just going to focus on the basic definitions. Let's start with the definition of a Markov chain. We say that a sequence of random variables x0, x1, x2, and so on is a Markov chain if for all t, for any sequence of values c0, c1, c2, and so on that these random variables could possibly take on, the probability that xt is equal to ct, conditioned on the probability that xi is equal to ci for all I less than t, is equal to the probability that xt is equal to ct, conditioned on only the event that xt minus 1 is equal to ct minus 1. That is, this sequence of random variables is a Markov chain if the value of xt depends only on the value of xt minus 1. It doesn't depend on any of this earlier stuff. This property is sometimes called memorylessness. That is, if we think of t as marking time, the random variable xt doesn't remember anything before xt minus 1. Looking at this definition, a priori, the value of this probability here could depend not only on ct and ct minus 1, but also on t itself. However, there are many Markov chains where it doesn't depend on t, and such Markov chains are called time homogeneous. More precisely, a Markov chain x0, x1, x2, and so on is called time homogeneous if for all values a and b, and for all times t greater than or equal to 0, the probability that xt is equal to a, conditioned on the probability that xt minus 1 is equal to b, is just some value p sub b transition to a that only depends on a and b, doesn't depend on t. As we'll see in a moment, time homogeneous Markov chains are especially convenient to deal with. To illustrate the definition of a Markov chain, let's look at kind of a silly example. This example is also going to introduce a way of drawing time homogeneous Markov chains as directed graphs. So here's the example. Let's divide time into, let's say, 5-minute chunks, and let's let x sub t be equal to my activity in time step t. There are 3 possible values for x sub t, that is 3 possible activities I could possibly be doing. I could be working, I could be following links on Wikipedia, or I could be taking a 5-minute walk. The arrows in this diagram represent the probability of transitioning from one state to another. So for example, this 0.5 here means that the probability that x sub t is equal to following links on Wikipedia, conditioned on x sub t minus 1 being equal to working, is equal to 0.5. So what this Markov chain here is doing is the following. Suppose that I sit down to work for 5 minutes. After I've done that, there's a decent chance, 30%, that I'm going to continue working. However, there's also a decent chance, 50%, that I'm going to start following links on Wikipedia. There's also some 20% chance that I need to think about something, and so I'm going to take a 5-minute walk. If I go this way and start following links on Wikipedia, then there's a very good chance, 80%, that I continue following links on Wikipedia. I'm certainly under no circumstances going to go back to work, but there is some 20% chance that, again, I'll encounter something I need to think about and have to take a walk. Once I take a walk for 5 minutes, that kind of clears my head, and 100% of the time after that, I'll be ready to sit back down and get back to work. So we can imagine these random variables, x0, x1, x2, and so on, evolving sort of as we step around this graph with certain probabilities. We can also represent a time homogeneous Markov chain as a transition matrix. This is a square matrix where both the columns and the rows are indexed by possible values for the random variables xt. The entry that goes in the row indexed by some value a and the column indexed by some value b is just going to be the transition probability from a to b. A transition matrix is a convenient representation for a Markov chain since it allows us to write the distribution of xt in terms of the distribution of xt minus 1. More precisely, we can write the distribution of xt minus 1 as a vector. So let's do that here. So here when I say write the distribution of xt minus 1 as a vector, what I mean is that the 8th entry of this vector is going to be equal to the probability that x sub t minus 1 is equal to a. And the reason I've drawn this vector over here is because I intend to multiply it by this matrix. When I do that, I get some other vector. And the bth entry of this vector is equal, just because of how matrix multiplication works, to the sum over a of this value, the probability of transitioning from a to b. So that's just the probability that xt is equal to b conditioned on xt minus 1 being equal to a, times the corresponding entry over here, which is the probability that xt minus 1 is equal to a. Adding all of these things up, we just get the probability that x sub t is equal to b. Therefore, this vector that we get here is just the distribution of x sub t. That is, multiplying by this transition matrix is just going to take the distribution of x sub t minus 1 to the distribution of x sub t. And this can be really convenient. Returning to our example, the transition matrix looks like this. To see how we might use this, let's assume that this is the distribution of x naught. That is, with probability 1, I'm going to start working at time 0. Now I multiply this vector by my transition matrix and I get some other vector, which is the distribution of x1. That is, this is the probability distribution on my activities after one time step. We can do it again, putting the distribution for x1 over here, and get the distribution for x2. And more generally, if I start with the distribution for x0, and I multiply it by the transition matrix raised to the, let's say, 20th power, what I'm going to get out is the distribution of x20. In particular, if you check up on me after 20 time steps, or 100 minutes in this example, then the probability that I'm messing around on Wikipedia instead of, say, working on this lecture is going to be like 60%. So that's a brief introduction to Markov chains. To recap, a Markov chain is a sequence of random variables where x sub t, the tth random variable, only depends on x sub t minus 1, but not anything that came before it. When the probability that x sub t is equal to a, conditioned on x sub t minus 1 being equal to b, depends only on a and b and not on t, the Markov chain is called time homogeneous. Time homogeneous Markov chains can be represented as directed graphs and also as transition matrices. So that's all for this video. Thanks for watching.